Hey, Charles.
Hey, Michael. How's it going?
Not too bad. I'm very excited because today we get to talk about TD with control.
Okay. Is that what that yellow thing is?
That's intended to be a lightning bolt. I don't know. Somehow it just convergence, TD with control. It sounded like a superhero movie to me.
Okay. That makes perfect sense. So, why are you excited about this?
Well, so what we're going to talk about is how to not just learn values using update rules like TD, but to actually learn the values of different actions that we might take as a way of figuring out the right way to behave.
Oh, okay. I like that.
Yeah, and we'll even get really close to proving that these methods converge. That is to say, that given enough data over enough time, they actually do the right thing.
Okay. By the way, did you know that Convergence is the name of the 2015 company-wide event in DC Comics?
Whoa. Okay, so it is a superhero thing.
Yeah. Well done.
Does that mean we get paid for using their stuff, or does that mean that we have to pay for using their stuff?
I think it means that we have to pay them. So,
Oh, whoops.
time to raise tuition.
Can I do that?
There you go. Now everything's taken care of.
Ta-da. The difference between using reinforcement learning for control and using reinforcement learning without control is basically whether or not there's actions that are being chosen by the learner. And so just to make that make sense, let's swap back in the notion of a Bellman equation. So this is the Bellman equations without actions. This is what we've been talking about for the last few videos. You recognize the Bellman equation? Value of a state is the reward plus the discounted expected value of the next state.
Yeah. I mean, usually you write that with an A in there.
Right, right. But I said no actions.
Okay.
We're going to put an A back in just a moment.
Okay. That'll make me feel better.
Certainly when we were talking about TD, we didn't really have much of a notion of actions. We were really talking about a sequence of states that were being experienced and the rewards associated with them. And in fact, the update rule that we talked about, this is one of the update rules that we talked about, says that if we go from some state and we get some reward and we end up in some new state, then what we're going to do is our new value function estimate is going to be it's going to be the same as the old one, except for in the state that we just left, where we're going to move a little bit towards the reward we got plus our prediction, our discounted prediction of the state that we just landed in. So what update rule is this of the different update rules we talked about?
TD0.
Yeah, TD0 factorial. So what we need to do now is get control back into the picture here. And so we're gonna do that now. So here's the same idea, the Bellman equations and a learning update rule, but this time with actions.
Actions.
So in the action form of it, we have this Bellman equation, the Q form of the Bellman equation. QSA equals the immediate reward plus the discounted expected value of the maximum action in the resulting state. Okay, so when we actually land in that new state S prime, we choose the action that is best for that state.
Right.
But otherwise, this is really the same kind of update as before. And so we can translate this into a TD0-like rule using the same sorts of ideas, so that we're going to have a new estimate of the value function, and the way that we're going to change it as we go from one time step to the next time step is it's the same everywhere except for the state and action that we just left. We just took action A sub t minus 1 in state S t minus 1. And so that one we're going to update. We're going to move a little bit in the direction of the immediate reward plus the discounted value of the state that we landed in, st, where the value is taken. Is that better? It's taken with respect to the best action that we get from that state. Okay, so this is, again, the same update rule. The only difference is we got this extra little max in here to simulate the idea of choosing the best action from each state. All right, so what I'd like to argue here is that this Qlearning update rule is actually taking care of two different kinds of approximations all at one time. So let me step you through what those are, and then what we're going to do is understand how each of them works independently, and then use a result that says if these two things work independently, they're going to work together. So, all right, so here's the first idea. Notice that if we knew the model, if we knew the transitions and rewards, then when we go from some state, take an action, get a reward, go to a next state, we could actually use that to update the Q values simply by applying the Bellman equation.
Right.
All that's really happening there is we take the old Q value estimate and we update it in the way that the Bellman equation says we should update it at that particular state and action pair. And so we haven't quite argued that this works. We said that it works, but I want to dive into a little more detail on why this works. But I want to show that there's a second kind of approximation that's actually being used at the same time. So here's the second kind of approximation that's going on with the Qlearning update. It says that if we knew Q star already, we could use that to learn Q star, which now that I say it out loud seems kind of tautological.
I think it kind of is.
But I don't mean it quite so directly. What I'm saying is, let's say that we run the Qlearning update like this. We say we were in some state, we took some action, we got some reward, we ended up in some next state. We're going to update the Q value for the state action pair that we just left, moving it a little bit in the direction of the reward that we just got, plus the discounted value of the next state, ST, which for the purposes of this little update rule, we're going to use the actual Q values to get that estimate. So we're kind of cheating here. We're saying we already know the Q value at least for the next state, and we're going to use that to update the Q value for the state action pair that we just left.
Right, and that would work because since we keep applying truth to it, Q star being truth, eventually you have to kind of get closer and closer and closer to it.
Yeah, and do you remember there's an important property, though, that we have to have in terms of this learning rate?
Proper subscripts?
No, you can get subscripts wrong, and you can always fix it in post.
Mm-hmm. Well, what's that property, Michael?
Yeah, so what is the property? So this is just like in the TD rule where we said that if we have the learning rate sequence sum to infinity, but the squares of that sequence be finite, then good things happen. We actually converge to the right answer.
Right.
So in this particular case, if we know what the target is, if we know where Q star is supposed to be for the next state, we can use that to actually what we're really doing here is dealing with the expectation over next states, right?
Mm-hmm.
And we handle that by using next states sampled from the distribution, right? Because we're actually acting in the world.
Right.
And instead of actually computing this sum, we just do this successive averaging thing, and that's going to work out.
Right. And so with insanely high probability, you will move towards the expectation.
Yeah, like probability 7.
Yeah. Yeah, that's pretty insanely high.
That's pretty insanely high.
Mm-hmm.
Yeah, so the piece that we really don't have yet to build on is this first piece. Like, what is it that's making the Bellman equation update actually converge on the solution to the Bellman equations, or Q star? And so we're going to prove that next, and then we're going to show, or actually assert, that these two things can be tethered together in such a way that they're both going to end up converging in tandem.
Nice.
To make the notation actually come out relatively cleanly, to minimize the number of subscripts that I'm going to mess up, we're going to introduce a notation called operator notation, functional notation, and we're going to introduce in particular a Bellman operator. So Bellman operator is going to be a mapping, a transformation from value functions to value functions. Like, you give me a Q function, the Bellman operator will give you back possibly a different Q function.
Okay.
So it's a function from Q functions to Q functions.
Does this operator have to have any particularly interesting properties?
We're going to prove that it has some properties, but first let's define what it is.
Okay.
Boom.
Oh, okay.
So here's how we're going to define this Bellman operator B. We're going to give it a Q function, and the new thing that we get out, this B applied to Q, has the property that at state action pair SA, it's equal to the immediate reward plus the discounted expected value of the next state, where we look up the value of the next state using whichever Q function we were given as input to the operator. So Q goes in, BQ comes out. BQ is a new value function, a new Q function. Do you think you get that?
I think I do. I guess I don't know why we're going through this yet.
Oh, I'm not going to tell you that quite yet, but I just want to make sure that you get it by quizzing you.
No!
This notation is very succinct, and so we can actually rewrite some things that we've talked about already in this very nice operator-based form, and it makes it look smaller and neater and easier to work with. So just to try to prove that to you, the equation Q star, that's a value function, equals B applied to Q star is another way of writing something that we've talked about a bunch of times. So I was hoping you'd be able to fill that in here. And also the notion that if we define some value function Qt to be like a whole sequence of value functions where each value function Qt is defined as the Bellman operator applied to Q of t minus 1. These both are things that we've talked about and have names, and I just want to try to get you to connect those to each other.
Okay. I will do my best.
All right, so do you see what to do here?
No.
Okay, all right, so here's my suggestion. So remember, this b thing is just a bit of notation here. And what the notation is saying is that whatever value function you give it, you can replace this whole thing with a value function defined like this.
Right.
All right. And so imagine what happens if you actually plug all that in. If you actually take this bq star and replace it with the definition according to this operator definition above.
That says that Q star is actually equal to, well, that's the definition of Q star.
Ah, do we have a name for that?
Q star?
Sure, we have a name for Q star, but the equation that defines Q star.
Well, it's the Bellman equation.
Yay!
Oh, that was easy. Okay.
Woohoo! And you don't have to put the exclamation mark to get full credit for that one.
Oh, I don't know. I think you should require they put the exclamation mark or they don't get full credit.
No, I think it's okay.
All right.
In fact, anything that has Bellman in it should be fine.
Anything that has Bellman in it?
Yeah, like the Bellman identity, or the I don't know. I was trying to think of other sequels that have
The Bellman ultimatum?
yes, Bellman Reloaded. All right, so good. So with that kind of thought process in mind, can you do the next one? So we have some Q function. We apply the Bellman operator to it, and we get some new Q function.
Bellman update?
Yeah, it is a Bellman update. But this now you can think of as an algorithm. It's going to actually generate a whole sequence of value functions, one from the next.
TD?
No.
No. Well, then I don't know because I'm trying to. Oh, wait. This is value iteration.
Woo!
Yeah, I think I need extra exclamation marks for that. That makes perfect sense.
Yeah, so value iteration is this big algorithm, and it probably takes a page of code or whatever to write. But in this operator notation, boom, it's like you start off, probably to be more precise, you want to say something like Q0 equals the 0 value function or something like that. You need to initialize the value function, but then after that, you're just generating value functions from other value functions. That's exactly how value iteration works.
Yeah, and it would work even if Q0 weren't initialized to 0.
That's true. Yeah, but if we wanted it to be a complete algorithm, we'd have to sort of say where it starts and then how we generate new things from old things.
Mm-hmm. Well, it just starts with whatever happened to be in memory at the time.
I see. Yeah, that could run you into trouble, but probably shouldn't, as long as the types are correct.
Yeah, well, it doesn't matter. They're just bits. They're ones and zeros.
Yeah, but they better be interpreted as floating point numbers, because if you interpret them as like imaginary numbers or something like that, it could make the Bellman equation act strangely.
It doesn't matter. The operators will do the right thing. They'll just interpret them as floating point numbers or doubles.
Perfect. Okay, well then we're all happy. So I guess what I was hoping to do with this example is, convince you to develop an appreciation for this particular notation, this Bellman operator notation, because we can write stuff that we care about really, really succinctly.
Yeah, okay, I buy that, and it means that you'll be able to fit everything in on a slide,
which would be good. And look at how less I'm messing around with subscripts. It's very nice.
I don't know. I like your subscripts.
So we're going to define a special kind of operator called a contraction mapping, and we're going to say an operator is a contraction mapping if it has this property. So B is some operator, and it's mapping value functions to value functions. If it's the case that for all value functions, so all value functions f and g, and some multiplicative factor gamma, which is less than 1, if it's the case that the distance between b applied to f and b applied to g has to be smaller than or equal to gamma times the original distance between f and g, then we say that b is a contraction mapping, that it's causing things to get closer together, tighter together. So this notation here is sometimes called the infinity norm, the max norm, and all it's doing is saying this is a function of states and actions. So which is the largest? What's the largest state action pair in terms of absolute value?
Okay, so that's just saying what's the maximum value that the function q can have.
Or that it currently has. Yeah, that's right. So when we write f minus g max norm, really what's this saying is what's the biggest difference in q values between f and g? And this is corresponding q values.
Mm-hmm.
All right. So f minus g is saying what's the biggest difference between these two q functions at any state action pair. Whatever that largest difference is, we're going to multiply it by something that makes it even smaller. And we're going to say that for it to be a contraction mapping, it has to be the case that if you apply that mapping to f and you apply that mapping to g, the distance between the resulting functions is even closer together than they started.
And that makes it a contraction mapping. Okay.
Yeah, so this is how we're going to define a contraction mapping. And this is going to give us all sorts of nice properties, and it's also going to happen a lot in the kinds of operators we get in reinforcement learning.
So just to be sure that I have this right, since the infinity norm finds the biggest value, and here you define the difference between two functions, at least the infinity difference between two functions being wherever their greatest distance is. It's certainly the case that over time, as we apply this operator over and over again, the point where their maximum is, the state action pair where their maximum is, might change every time, right?
Right, that's right. So this max norm is computing for the specific value function that it's given where the biggest value is, the biggest absolute value is. And that could be different on this side of the equation from this side of the equation. There's no reason that it needs to be the same over and over again. And in fact, when we're using B to be kind of like a value iteration operator, it does tend to move around a lot.
Okay. So you would expect it to move around a bit, at least as you're going through value space.
Yeah, exactly. And however, let's not worry about that quite yet. Let's actually do some contraction mapping examples on just scalar values where it's really easy to reason about them.
Okay, yeah, I think that would be cool.
All right, so we're going to play around a little bit with this idea of contraction mappings, but in a very simplified setting. We're going to look at, instead of Q functions, we're going to look at just scalars, just real numbers, x. So B is some operator that applies a number, that is applied to a number, and it spits out a number.
Mm-hmm.
And I've defined 4 different kinds of B's here, and some of them are contraction mappings, and some of them are not. And we have to figure out by using the definition of contraction mapping which are which.
Okay, so let me just make certain that I have this. So the way you define contraction mapping before, you said there would be these two functions, and you basically want to see if they get closer and closer to one another.
Yep.
As you apply the operator. But here, the function is just a thing that, instead of being like a Q value with all these indices, it's just a number.
Yeah, you can think of it as being a single state, single action, right? It's like an MDP that has one state and one action. So it's just a number.
Okay, so it's just a number. All right. And so I just want to see if there's some gamma that I can choose between 0 and 1, inclusive of 0, non-inclusive of 1, that as I apply these operators, x over 2, x plus 1, x minus 1, and x plus 100 times 0.9, that will just get smaller and smaller and smaller and smaller and smaller, closer, closer, and closer together. Okay, I think I got it.
Okay.
All right, so let's do the quiz. Go.
All right, you ready to answer these questions?
Yes, I think I am, and I think I know the answers. I think they're yes, no, no, yes.
Great, that's actually correct. You want to tell us how you can actually argue that?
Well, no, but I'll do it anyway. So let's take the ones that I think are pretty easy, 2 and 3. So
okay,
without even coming up with an example, I think it's pretty easy to see that those aren't contraction mapping, and here's why. So let's imagine I started out with two functions. Let's say they were, I don't know, 6 and 8.
Okay, so we're going to say x equals 6 and y equals 8.
Yes, where y is the other function. Well, what's the difference between them? It's 2.
So just let's make sure we're applying this in the right context. What we want is that the distance before we've applied any operator to them is going to be bigger than or equal to the distance between them after we've applied the operator.
Right. And it has to be that gamma is less than 1. This actually becomes important.
That's right. All right, so you did x minus y is 2.
Right. Well, x minus y is 2. Well, when I add 1 to both of them, that'll just become 7 and 9. But the difference is just 2.
Okay, so I do buy this, that adding 1 to something shouldn't be a contraction. But it seems like subtracting 1 from something should make them smaller.
Right, except it makes both of them smaller in exactly the same way. And so you're basically keeping the distance between them constant.
Ah, good point. All right, so, and in fact, the same example works here. So 6 and 8 are 2 apart. 6 minus 1 and 8 minus 1, or 5 and 7, are still exactly 2 apart. So 2 is not less than or equal to any gamma less than 1 times 2.
Right.
So yeah, so I agree that these are not contraction mappings, and the proof basically involved showing a particular value of x and y such that they're not getting any closer together. They're staying the same distance apart.
Right, and I think you could even prove that by just basically writing down the equation that relates x and y together, right? Y is equal to x plus 2. If I subtract a constant from both sides or add a constant to both sides, it doesn't change anything.
Very good.
Right. So for the first one, x over 2, here's my thought process and kind of the proof that I ran through in my head, and then the realization that I had that made 4 actually easier as well. Okay, so why don't you erase that, and I'll give you an example what I was thinking. All right, so the x over 2 thing, I thought, oh, we're going to just keep dividing by 2. So let me come up with an example in my head, and I thought, oh, I should use a power of 2 because then I can keep dividing by 2.
Well, hang on, hang on. So, well, okay, we'll let you step through that, but that's not gonna get us all the way there.
No, it's not, but
But go ahead, let's do it anyway. All right.
well, I was just going through my thought process.
Okay.
Right. So just for the sake of thinking out loud, let's just say x is 16 and y is 32. So what's the distance between them? Well, it's 16.
Good.
Now when I divide both of them by 2, I get 8 and 16.
Right.
And the distance between them is 8.
Good. All right. And 8 is definitely less than 16.
Right. But then I realized, oh, this is actually pretty simple. I'm glad I chose a power of 2. That basically the distance between x and y at any given, let's say, time step is just going to be, I chose x to be some 2 to the n and y to be 2 to the n plus 1.
Right.
And then if I divide both of them by 2, then the new distance will be 2 to the n minus 1 and 2 to the n.
Sure. But this is only showing that it works for things that are like consecutive powers of 2, which is not what we need. We need it to hold for all x and y.
Right. But that was the process that I went through in my head to kind of show that this will keep working. And then I realized, oh, what's really going on is I'm taking my value x and I'm making it smaller.
Sure. But that's true of number 3 also.
That's true, but I'm making it smaller in a geometric way.
Okay.
You don't like that?
I mean, to me, the easiest way to step through this is to just do the algebra, to say that, so bx is x over 2, by is y over 2.
Yeah.
So the absolute difference between them is actually equal to 1/2 of the distance between x and y.
Yeah, that's fair.
Right. So I'm just factoring that, and this gives us exactly what we want, which is to say that the difference before compared to the difference after applying the operator is less than or equal to some less than 1 value multiplied by the old distance.
Yeah, that makes sense because that's exactly what I was doing when I went from 16 to 32 to 8 and 16.
Exactly. Yeah.
I noticed the distance was cut in half every single time.
Right.
Okay. But that general thing is going to work for number 4 as well, right? So the first thing to do to make that really easy is to realize that although you've written it as x plus 100 times 0.9, so I could rewrite that as x times 0.9 plus 90.
Good.
Right. So the x times 0.9 part is going to keep reducing by exactly the same argument that you did before. I could take out the 0.9 and show that it's going to just keep getting smaller.
Mm-hmm.
So that part's going to get smaller. And since I'm adding a constant every single time, it's not going to change the actual distance.
Good.
So it will continue to get smaller.
Yeah, that's right. So and so algebraically, if we have whatever x and y were before, after we apply this operator, as you just pointed out, it's actually going to be 0.9x minus 0.9y, plus 90, but then they're going to get subtracted. And so this quantity is equal to 0.9x minus y. We can just factor that out. So whatever the distance was before is actually contracting a little bit. It's getting a little bit smaller, 9/10 the size of what it was before.
Right. And so there are two things there. One is adding a constant, whether that constant is positive or negative, doesn't change the distance because they're going to cancel each other out. That's why 2 and 3 don't work. And then multiplying your function by a number that is less than 1 will make them get closer and closer together, which suggests that if we were instead to multiply them by a number greater than 1, or actually 1 or greater, you would end up with something much, much, much worse. If we get bigger and bigger and bigger, it'd be an uncontraction mapping.
Expansion mapping.
Yeah, it's an expansion mapping. I like that.
Great. Okay, nicely done.
Yeah, cool.
All right, so one of the reasons that contraction mappings are really cool is because they have some very nice and convenient properties. So let me state those properties, and then maybe we can figure out why and how it has these properties. So the properties are, if B is a contraction mapping, we know that B is a contraction mapping, and that means that any two functions that we pump through it are going to get closer to each other than they were before you pumped them through. Then, first of all, if the equation f star equals bf star, sometimes called the fixed point equation, has a solution, that there is some f star that you can plug in to B that causes it not to change, right? So whatever f star was before, after we put it through B, it stays the same as it was. It's a fixed point.
Mm-hmm.
And there's just one of those. It's unique. So just setting up this equation says, okay, it has a solution, and we can just call it F star because there's only one that works.
Okay.
And a second property is that we can actually converge to F star by doing this kind of value iteration idea, that we start off with some value function, we push it through the operator, we get a new value function out, we push that through the operator, we get a new value function out. We just keep doing this over and over and over again. And that the sequence of value functions is converging in the limit to the solution, F star.
Okay, so that makes sense, Michael. Here's a question for you. If one is true, and I know that B is a contraction mapping, then doesn't 2 follow from that?
Well, one is true. but yeah, it's actually not so hard to see 2 being true given that. So here's the idea. So let's say we have some F star, and we know that B is a contraction mapping. Then let's look at what happens to Ft minus 1 compared to F star. All right, so by the definition of a contraction mapping, we have this property, that there's some gamma less than 1 such that for any 2 value functions, they're going to get closer together after we apply the operator. But the 2 value functions that I choose are f of t minus 1, the value function that's coming out of this sequence, and f star, the fixed point.
Mm-hmm.
All right. So just by virtue of being a contraction mapping, we have to have this be true. But let's look to see what this is actually equal to. So what's b of f t minus 1?
Ft.
Yep. And what's b of f star?
F star.
Yeah. So we're getting closer and closer and closer to f star. This sequence, however far it was from f star before we do the operator, the next time we do the operator, it's at least 1 minus gamma of the way to f star. So we just keep repeating this over and over again, and they're going to be equal.
Right, that makes sense. Okay, so if B is a contraction mapping and a unique fixed point exists, then you have to get there eventually.
Right, and then showing that the fixed point is unique is the same kind of argument as here. Like if we have 2 different fixed points, then, right, so if we have 2 different fixed points, that would mean that we'd have an f star that satisfies an equation like this and a g star that satisfies an equation like this. And that means if we take f star and g star and we put them through the B operator, they're not going to get any closer together because they're going to stay exactly as far apart as they were. And that violates the notion that it was a contraction mapping. So there can't be multiple fixed points.
That's beautiful.
All right, so now that we have a notion of contraction, we should apply contraction to our favorite friend, the Bellman operator.
I do not use contractions.
Oh, I see what you did there.
Thank you.
My spouse is an obstetrician, and so sometimes she worries about contractions as well.
I think we could probably do this for an hour. But let's say we contract it.
Ah, nicely done. So, good. So, right, we want to apply this notion of a contraction mapping to the Bellman operator. In other words, we want to show that if we have a Q function Q, and we apply the Bellman operator to it, then, well, in particular, if we have 2 Q functions, Q1 and Q2, the distance between them after applying the Bellman operator is less than or equal to gamma times the distance before we apply it. So by applying it, we move these 2 Q functions closer together.
Sure.
All right, so the first thing we're going to do is unpack the definition of the max norm. And so in this case, in the case of Q functions, what that really means is we're going to maximize over all state action pairs the Q value of each of those state action pairs, difference and absolute value. And that leaves us in a good position to be able to unpack the definition of the Bellman operator itself over these 2 different Q functions, Q1 and Q2. So all I did here is substituted in for the Bellman operator the definition of the Bellman operator as it's written up here.
Mm-hmm.
All right, since we're computing the difference between Q values for the same state action pair, they're going to have the same reward, and then they're only going to differ really in the value of the resulting state.
Mm-hmm.
So we can cancel out these 2 rewards. We can actually factor together these gammas and the summations, which are the same in both cases, and we get down to the maximum difference over all state action pairs of the absolute difference between the discounted expected value of the next state and the value of the next state being for Q1, the max over all actions of the value of state S prime at Q1, and for Q2, the maximum over actions of the values at state S prime for Q2.
Oh, because you can't.
So why can't we just keep factoring it? Yeah.
Because they're different A primes.
Right. So do you see why I didn't go one more step here and actually combine these two maxes together, even though we combined these two sums together?
Yeah, because even though you wrote A prime both times, they're two different A primes.
Right, right. So this is the action that maximizes the Q value for Q1, and this is the action that maximizes the Q value for Q2, and they may have different max actions.
Right, even though they both end up in S prime.
They start in S prime. That's right.
Well, they start in S and they end up in S prime.
And then we're choosing the action in S prime.
That's right. Okay, yeah, that makes sense.
So let's just make a little room here, and we'll copy this equation down one more time. But this time what we're going to do is, instead of considering this weighted combination of the Q values at state S prime, weighted by the probability of reaching S prime, let's just make it simpler and just worry about the S prime where the difference is largest. Since this is a weighted average or a convex combination, it can't be any larger than the biggest difference at any S prime. So we're going to do that. We're going to copy that down, max it over S primes. And we don't need to include the max over A and S anymore, because you'll notice this expression doesn't even have A and S in it anymore. Right. So actually, by considering this kind of worst case version, we don't have that max anymore.
Mm-hmm. And that gets us from an equal to a less than an equal.
This gets us from an equal to a less than an equal. That's right, because we're bounding it. It could actually be a bit wider here. We're considering the worst possible next state in terms of the difference between these Q functions.
Okay.
And now you can see that it's actually getting pretty close to where we want to end up. The main difference, in fact, let me rewrite this max norm equation out. So when we write that out, we get gamma times the max over state action pairs. And I'm going to write S prime and A prime just to make it easier to match up with the other equation. It's whatever, however we're indexing over the state action pairs that make up Q1 and Q2. So this max norm is really just the max over those of the difference between the two Q functions. And this is where we are at the moment. We have something like gamma max over S prime, and these maxes are kind of trapped in the absolute value. It would be really nice if we could move these maxes out of the absolute value. And have it this way. So now the A primes actually match up. Here, this is the max action according to Q function Q1, and this is the max action according to Q function Q2, and it would be good if we could just talk about them together. So this is kind of, to me anyway, this is the most fun, most exciting, most interesting step, because this turns out to be true, right? That we can actually move these maxes out. And then we get a valid sequence. So I'm going to focus in on this step in a moment, but let's just accept it for the time being that we can move these maxes out. Now we've actually completed the algebra that we needed to complete, that the difference between the two Q functions after we apply the Bellman operator is actually less than or equal to gamma, something smaller than 1, times what the distance was before we apply the Q operator. The B operator. So this is in fact the contraction property of the Bellman operator, of value iteration.
Wow, so Bellman and value iteration converges. Except for this magical step you're about to explain to me.
Except for the magical step, yeah. And the magical step is fun because I alternate between seeing it as completely obvious and like, of course this is true, and being completely mystified and don't understand how it could possibly be true. And my brain just sort of flips back and forth between those, kind of like a Necker cube. So let's dive in and make sure that this property holds, knowing that once we establish that, we get the whole chain, we get the whole contraction operator thing. We get all the power of contraction operators in when we're doing Bellman updates. This is the property that we would like to hold for max. The max needs to be, I'm going to call it a non-expansion. It looks just like the contraction property, except there's no gamma multiplier here less than 1. So it could be that we have equality here, and it could be that we have less than. But we have this kind of non-expansion sort of thing going on, that when we apply max individually to these two functions f and g, we get something that's going to be, the difference between those is going to be closer together than if we actually just take the max over the entire differences between f and g. So I don't know how crystal clear this is, but I think it might help to do a concrete example.
It is not crystal clear. Wait, quick clarification question. So you have max A, f of A, max A, g of A, but just like before, those are actually two different A's?
That's right. In fact, there could be 3 different A's, because this thing on the right-hand side could be yet a different A.
A. Okay.
So this is all very abstract. So let's actually just write down some concrete numbers. And imagine we have two functions, f and g, defined over the same set of a values, a1, a2, a3, a4, a5, a6, a7. And I don't know, just fill them in this way. F of a3 is 1, g of a5 is 8, and so on.
Mm-hmm.
Do you get that?
I do.
Good. So, quiz. Just fill in what these quantities are in the case of these particular numbers, and just make sure, we want to prove that this holds for any f and g, for all f and g, but let's just make sure that it holds for this one first.
Okay. I like this quiz because this one I think I can actually do.
Yeah, it's not hard, but it starts to make you think about the relationships between the numbers in the two functions.
Well, you can try to make me think about it. All right. Go.
Can you compute these quantities for me?
Sure. So I got to find the max a of f of a. So I just have to find the maximum value for f, and that is 9. Happens to be at a2.
That's right. Happens to be at a2.
And the maximum value for g is 8, which is at both a3 and a5.
Good. All right. So then what goes in this box?
9 minus 8, which is 1.
The absolute value of 9 minus 8, which is also 1.
Yes, that's amazing.
And the other box?
So that requires a little bit more. I have to figure out what the maximum absolute difference is for each a. So I'm just going to do that. We're going to start at a1. So 7 minus 5 is 2. 9 minus 3 is 6. 1 minus 8 is 7 for the purposes of this discussion. 0 minus...
Well, because it's absolute value. It's fine.
It's absolute value. 0 minus 1 is 1. 6 minus 8 is 2. 3 minus 5 is 2. And minus 2 minus 5 is 7.
Good.
And let's see, the maximum value there is 7.
All right. And just to make sure, is 1 less than or equal to 7?
Most days.
There we go. All right. So good. So we verified that this theorem at least holds for this one example that I kind of made up at random.
Well, and then we just simply say it's true for one example, it's true for two examples, and then we're done, right?
This is what? Induction?
Yeah.
Yeah, I don't think we can do that. I think we actually have to do it by deduction.
Okay.
So here's what we're going to do. It turns out that it's sort of complicated to keep track of where all the maxes and the differences are and the absolutes and blah, blah, blah. So we're going to make a simplifying assumption, which is that the largest value in our f function is bigger than or equal to the largest value in our g function. And I'm going to say we're going to assume that without loss of generality. Why is that okay?
Because if it weren't true, we just swap f and g around.
Yeah, that's all. I mean, we'll just call f, of the two functions that we're comparing, call f the one that has the larger max.
Mm-hmm.
Or larger or equal. I guess if they're equal, if the maxes on the two are equal, then it doesn't matter. But we want f to have the larger of the two. And what that's going to do is going to simplify some of our thinking with the absolute value symbols, because otherwise the case analysis gets really tedious.
We can't have that. Okay. I can't wait to see where this goes.
All right. So ultimately, we're going to be trying to compare this quantity to this quantity. And so let's start off writing this quantity on the left, and then we're going to reduce it step by step until we get the quantity on the right. So here's where we start. What can we do with this? Well, given that we know that the max of f of a is bigger than the max of g of a, because that's what we were assuming when we named f and g, we can get rid of the absolute value signs. Yay! Now, because we're finally going to come clean on this issue that you were talking about before, which is that these are kind of different a's, and it would be good if we gave them different names. So let's actually do that. Let's actually say that a1 is argmax f of a, and a2 is argmax g of a.
Mm-hmm.
So now we can rewrite this difference, max a f of a minus max a g of a, much more simply, as just the difference between the corresponding values in the function.
Sure.
All right, so if you let me get away with that, now you're in trouble, because the next step is going to follow pretty easily from this, but it's going to take us into a whole new realm. So now we said that this quantity is equal to the difference at a1 of the f function and the value at a2 of the g function. So since this a2 was chosen to maximize the g function, then any other a that we could substitute in here, let's just say a1, can only make this smaller, or it can make it no bigger.
Right.
Right, so the GA2 versus GA1, GA1 is going to be smaller than or equal to GA2.
Yeah.
But since we're negating that in this equation, that means it can only make this quantity smaller than or equal to the previous quantity.
That's kind of amazing. That's a neat trick.
Right. So, intuitively, like does this piece feel okay intuitively now? Essentially, what we're doing is we're taking the place where f is maximized at a1 and the place where g is maximized at a2, and we're just sliding over to a number that's, well, here, think of it this way. So I find this little piece helpful. So because of our without loss of generality statement, we have that, if we think of this as a number line, we have the f value at a1 is the largest thing of all. It is the king.
Mm-hmm.
The g value of a2 is some other large value, but not as large as f of a1. So if we switch from GA2 to GA1, we have to be going down, or at least not up.
Mm-hmm.
And so if we look at the difference between these two quantities and the difference between these two quantities, the difference can only have gotten larger. And that's what this equation is showing, that the difference can only have gotten larger when we substitute in the a1.
Well, that's not true. It could stay the same. So f of a1, g of a2, and g of a1 could all be the same number. But g of a2 cannot be bigger than f of a1, and g of a1 cannot be bigger than g of a2.
Good.
No, that's really clever. So, I mean, this is cute. This gets you a way of going from two completely different variables to one variable.
Right.
That's awesome.
Now we're almost home free. So the first thing I want to point out is that we can reintroduce these absolute value signs without killing anything.
Mm-hmm.
Well, because we can. This is a positive quantity, and so taking the absolute value doesn't change it. So the last little thing to point out is that if we take the max of this same quantity, substituting in different values of a, this can only get larger, or no smaller, because this a that we're maxing over includes a1. So we can definitely achieve at least this value, but it's possible that some other action will let us achieve an even larger value. But by maxing, we can't have it achieve a smaller value. I mean, it could achieve a smaller value, but it'll be at least, the max will be at least as big as what we get for A1.
Right.
And with that in place, that actually completes the chain of inequalities from here to here. So we get this non-expansion property for the max operator. Here, the max operator is being used here as sort of a way of summarizing these functions f and g.
Okay, so let me just say that last thing back to you, make certain I got it. So I'm with you all the way to f of a1 minus g of a1. You went to the absolute value signs. That's pretty easy because we already knew that value was positive. That difference was positive by construction. And then that last step, you've noticed that the difference between a1, f of a1 and g of a1 is some number. You're maximizing over all possible a's you could stick into f and g. It has to include a1 by definition, which means the max might be bigger, but it couldn't be smaller than a1. And so therefore, you're bounded from above.
Excellent. Good. Yeah, well said.
That's really cool. Now I've forgotten why we did this.
I find that's often true for me as well. That this requires enough of my attention that I lose context. But the context was that we had this step in our proof that the Bellman operator is a contraction. We needed it to be true that summarizing the Q values at a given state using a max was going to leave us with something that is no farther apart than the maximum difference between the two functions that we started with.
Okay. Yeah, I remember that. Maybe you can show me the equation again.
And in particular, it was this step right here, where essentially we had to, one way to think about it is move this max out of the absolute value. So if we compare that to what we just proved, that's what we did. We kind of moved the max out of the absolute value.
Right. That's awesome. Good. Okay, so I get it. So the Bellman operator is a contraction operator. Value iteration works.
Yes, indeed. Now, I went through a phase of my life where I got really kind of fixated on non-expansions and identified a whole bunch of other operators other than max that are also non-expansions. And that actually gives us a way of analyzing a whole bunch of other kinds of decision processes. Right? So not just these standard Markov decision processes where we're trying to maximize expected reward, but we can do a lot of other things, and this same kind of proof is going to end up holding. So we're going to get back to that in a moment, but first I want to talk about how we use this property, now that we've established it, to prove the convergence of Qlearning, right? To prove that this interesting way of updating the Q values over and over again in the face of experience actually does, in the limit, lead you to getting the solution to the Bellman equation.
Okay.
What I'd like to do now is step through a statement of a theorem. We're not going to prove the theorem. That's really up to people like Csaba Szepesvári. But we're going to state the theorem and understand the theorem well enough so that we can apply it to showing that Qlearning converges.
Okay.
So the first thing we're going to do is, just to make things simpler to write down, we're going to say that Qlearning and update algorithms like that are going to update all state action values on all time steps. However, if it's a state action value that doesn't actually correspond to the current state action pair that we just experienced, then we just set the learning rate to 0, right? So that just means leave the Q values alone except for in the state action pair where you actually just experienced and got a transition.
Okay.
This is the beginning of the statement of the theorem. So we're going to say B is going to be some contraction mapping. So this is going to be the Bellman operator ultimately. Q star equals BQ star. That's the fixed point. That's the solution to the Bellman equation. So Q star is like Q star.
Okay.
And let's imagine that we've got some sequence of Q functions that starts off with Q0. And the way we're going to generate the next step from the previous step is we're going to, we have a new kind of operator, B sub t. B sub t is going to be applied to Q sub t, producing an operator that we then apply to Q sub t. And that's what we assign QT plus 1 to be. So in the context of Qlearning, this is going to be this is essentially the Qlearning update, but we're going to separate out the two different Q functions that are used in the Qlearning update. One is the past Q function that we're using to average together to take care of the fact that there's noise in the transitions. And then the other Q function is the one that we're using in one-step look ahead as part of the Bellman equation. But we'll get to that in a moment. But here's the cool thing, that this sequence of Q functions, starting from any Q0 that we want, as long as we keep applying this, is going to go to Q star, yay, as long as we have certain properties holding on how we define these B sub t's. So here's the first property. The first property says that for all Q functions, U1 and U2, and you see I used Q function and U together. Just because, you were you thought it was funny that I kept saying Q function and Q. So now I said Q function and U. All right, for all Q functions U1 and U2 and state action pair SA, this is true. All right, what the heck? So what's happening here? We're taking this B operator, applying it to U1 to get a new operator that we apply to Q star, and we compare that to that same operator BT applied to U2. Whatever operator we get out of that, we also apply to Q star. What has to be true, what we need to be true, is that this is going to be less than or equal to 1 minus the learning rate times the difference between the U functions. So this is a non-expansion property again, right? That the update rule, that the operator that we're using to modify the inner value function of the B is going to have this averaging property to it, that it's that what we're ultimately doing is computing the expected value. That's not exactly what this says, but that's how it's going to be used.
Okay.
But the important thing here is that it just doesn't make things get farther apart.
Okay. By the way, I just want to say I really appreciate your proper use of farther instead of further. It makes me very happy.
I try really hard when I'm talking to you.
Thank you. I appreciate that.
All right, so here's the second condition that has to be true, that for all Q functions Q functions U, and state S action A, we need another kind of, well, in this case, contraction property to hold true. Our gamma is sitting in there. Gamma is less than 1. See?
Mm-hmm.
And what we're saying is that if we hold fixed this U value, this value that plays this role in the operator, and the other one is Q star and Q, that we actually get a contraction of Q towards Q star by applying this operator in both cases.
All right.
All right, so we're almost there. And lastly, we're going to need our standard condition on the learning rates to hold, right, which is that they sum up to infinity and the squares sum up to less than infinity. But there's something hidden in this definition. It took me a long time when I read the first proofs of this. Like, no, this can't be true. In fact, what's happening here is that given that we set the learning rate to 0 when there's state action pairs that we're not visiting, the only way that this sum of learning rates for state action pairs is going to be infinity is if we visit every state action pair infinitely often. So this is, not only is this saying something about how the learning rates have to change, it's giving an additional constraint on how we have to visit state action pairs.
Wait, so then if that's true, if that gets you infinity, why doesn't that get you the squared? Why does that still get you the squared less than infinity?
Well, so the infinity and the squared less than infinity is here because we're going to be doing the standard kind of averaging trick, and we need the learning rates to decay the right way. But what I'm pointing out is that in addition to that condition, which we generally need when we're doing convergence of stochastic things, we also have an additional constraint that's hidden in here, which is it's saying we have to visit all state action pairs infinitely often. If we don't, then the sum of the learning rates is not going to be infinity. It's going to be something finite.
Oh, I see. No, 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 that's right. That makes sense. That makes sense. Oh, so cool. So basically, our algorithms will converge so long as we take an infinite amount of time.
Well, I mean, convergence is an infinite amount of time kind of thing, just to
Mm-hmm.
be fair.
Mm-hmm. No, it's very, very satisfying.
Later in the class, we'll talk about some results that actually hold, believe it or not, in finite time. But this result is intended to hold in infinite time.
Mm-hmm. I'll believe it when I see it.
All right, I want to try to explain this convergence theorem specifically in the context of Qlearning. It's intended to be general and apply to lots of algorithms of this form, but mostly we want to use it to show that Qlearning converges. So let me express Qlearning as an update rule in the form of this kind of weird BT operator notation that was used in the theorem. Okay, so BT is the operator that we're going to use to update the Q function on the T time step. And so given that we know that we're on the T time step, we know that we're in some state st minus 1, took some action at minus 1, ended up in some new state st, having received reward rt. All right, so what I'd like to kind of argue is that this strange definition of the operator BTQ is exactly the Qlearning update. So let me try to argue that. So this looks a lot like the Qlearning update, right? That says that we're going to take the Q function at SA and we're going to move it a little bit towards the immediate reward plus the discounted value of the next state, that much toward where, with the old, away from where that old Q value was. So the only thing that's different between the Qlearning update and this is that we've separated out two different Q functions, this W thing and this Q thing. Q is using to play the role of essentially the Q function in the state action pair that we just left, and
Mm-hmm.
W is playing the role of giving us an estimate of what the Q value is at the state that we just arrived in. And in regular Qlearning, those are the same, but we're now separating them out because the theorem is going to find that easier to swallow.
Okay.
All right, so you buy the fact that this is Qlearning, just in a slightly different notation?
Well, it certainly is if W and Q are the same, which is what you just said.
Yes, certainly the case now that W and Q are different. But you're saying it is Qlearning when W and Q are the same?
Isn't that what you said?
Yes.
Okay. So yes, that's what I'm saying.
Great. All right, so now what we want to argue is that this definition of the update rule causes the things that we needed to be true for the theorem to be true. All right, so let's start with condition 1. Why is this true for the learning rule defined this way?
But is that a question or you that's rhetorical, right?
It was intended to actually be a question. So let's look at what needs to be true of this learning rule. What needs to be true is that if we have essentially if we did this update in the form of knowing what Q star was and use it as our one-step look ahead here, then what do we want to be true? What we want to be true is that if you give me any two value functions, they're going to get no farther apart. In fact, they're going to get closer together if the learning rate, if we're actually updating that particular state action pair and the learning rate is non-zero, they should be getting closer together. So why is that the case? Why is it the case that if we do this update at a state action pair, doing our look ahead with Q star, that everything is sort of moving towards one particular answer? It's moving towards a particular answer. Do you know what it is?
Q star.
It is moving towards Q star, but in particular, it's trying to compute the expected value of this one-step look ahead, where the expectation is taken over at all possible values of ST.
Mm-hmm.
So it's essentially doing the averaging part of the Bellman equation, and the reason that works is because, well, that's sort of how things converge if you let learning rates converge, and we've talked about that in previous lessons.
Mm-hmm.
So all this rule is saying is that if we knew where we were going, we could use this update rule to average out all the stochasticity that we get from on different trials taking a step from a state and ending up in a different state because of the stochasticity of the transition function. So that's all this is saying, is that we can smooth out the stochasticity in the transition function using the rule that we're worrying about.
Okay, that makes sense.
All right, so that explains how that first condition is satisfied, that it's basically taking care of the averaging over noisy transitions. This second condition is going to turn out to be, well, let's find out what it's going to turn out to be. So what we're doing here is we're saying, let's apply this operator, this BTQ operator, or BTQW operator. And the condition that we need to have hold is that for any Q, U, S, and A, that if we hold this U fixed, right, which is in the Qlearning equation, is going to turn out to be the Q itself, and only vary how we're computing our one-step look-ahead, right, how we're estimating the Q values of states that we are moving to one step from now, that the difference between those two Q functions, in this case Q star and Q, is going to get smaller after we apply this operator than before, which is an example of what property? Like, what is it about the operator that we're counting on for this to be true? That before we do the one-step look ahead, they're some distance apart, but after they're closer.
Actually, I'm not sure.
So, however far apart the value that we're using as a one-step look ahead, however far apart it was before, that after we apply this rule, it's closer together.
Right, and they will be because you're moving in the direction of what the one-step look-ahead operator said.
Right, and so what property the one-step operator, what property of this equation is giving us that? It's the contraction property. All right, so the fact that this update has the form of a contraction is what gives us this property being true. That after we apply an operator, things get closer together.
Mm-hmm.
So, and then the third condition was just the condition on the learning rates, and we need that for any kind of Qlearning algorithm anyway. So at the end of the day, by separating the Qlearning update equation into kind of using two different Q functions in two different ways, we can prove properties of both of them. One is playing the role of averaging out the stochasticity, so that we're sort of acting as if there are expected values in here, even though there's not. And then given that, the other one is acting like the value iteration operator, the one-step backup, and is contracting with respect to the value function that you used. So the Q functions are being used in two slightly different ways. We prove that both of them hold, and therefore this theorem gives us that the whole iterative algorithm is going to converge.
Right.
So this is all really just a long way of saying, hey, look, because Qlearning can be forced to fit into this scheme, it's guaranteed to converge in the limit.
All right. So Qlearning converges.
Qlearning converges.
I mean, I guess we knew that.
Yeah, we knew that. And in fact, there's a long literature where people have proven essentially this result over and over again in slightly different ways using different tools. The thing that I like about this proof is, well, first of all, I read it because it's in a paper that I wrote. But second of all, it breaks things down in this sort of modular way that we're going to be able to reuse to prove the convergence of other Qlearning-like algorithms. And that turned out to be important to prove, for example, that Qlearning in game scenarios also converges.
Huh. But that's in the future.
That's in the future.
Are you going to reprove this all over again when we get to the future?
No, we don't have to, because the generalized theorem holds in both cases.
Nice.
That's the beauty of the generalized theorem. We never have to look at this again.
Well played, sir.
All that's going to matter is, well, it's going to matter that that the operators that we use for updates are contraction mappings.
Okay.
And as long as we take care of that, things are going to be great. Oh, sorry, non-expansions. As long as the kind of the thing in this position here is a non-expansion, all will be well.
Good. So well played. So we went through all this so we never have to go through it again. I like that.
That is exactly the thought. Yeah. And in fact, even missing all the details of this, I just wanted you to be aware of the fact that these details exist. The way that we actually use this is at a much higher level of abstraction, where we just say, hey, we can write down what we think the Bellman equation is. We can prove that the operators that we're using here are non-expansions, and we're done.
And we inherit everything else. Yeah, it's just like knowing that the sum of the alphas should go to infinity, but the alpha squared should not go to infinity. Once we know that, then it helps us to decide whether to choose this learning rate or that learning rate. It's the same thing. We can't just substitute max with any arbitrary thing we want to because it might not be, it might be expansive instead of non-expansive. But so long as we're smart about the things that we pick, we know that things are going to converge.
Exactly. And so let's maybe go through some examples of that as a quiz.
Sure.
All right, so now we're going to take what we just learned and think about what generalized MDPs might mean. So generalized Markov decision processes. So the Bellman equation for generalized MDPs looks like this. Q star SA equals RSA plus gamma times, kind of a summish thing over S prime of a maxish thing over A prime of Q star S prime A prime. So basically all I'm trying to say here is that we can take out, well, we can substitute various things in for this kind of plus operator and this times operator, and we get different sequential decision-making problems that come out of it. So just to make sure that that you understand what I'm talking about, let's do the first one together here. The first idea here is that we're going to replace this plus symbol with a sum over all S prime of the probability of reaching S prime times, and then whatever function we're plussing, which in this case is the X thing applied to Q star. So the X thing here is written to be the max operator. So max over all next actions. Well, it says F S prime A prime, but here we're going to be substituting in the Q star S prime A prime. So if we were to actually do this substitution in the first line, put this summation thing instead of the plus thing, and this max thing instead of the kind of times or X thing, what decision process sort of thing would we get from that?
That's just a regular MDP.
Yes, that's just how I would have said it. So it just gives us back the ordinary Bellman equation for MDPs. It's just, again, kind of a weird way of writing it, but the point is that we're going to allow different kinds of operators to be substituted in here, and we're still going to get very reasonable things out, things that we can run value iteration on, things that we can run Qlearning on, and so forth. So, all right, so if you think you get that, let's do the rest of this as a quiz. But basically what I'd like you to do is for each line here, if we were to do the substitution, where the plus operator is defined here and the times operator is defined here, what kind of decision process would we get out of that?
So I think I follow that. So let me ask a question. I'm looking over these, make certain it all makes sense to me. So I think I get what you're saying, right? So in the regular MDP, we have an expectation over maxes. And so the first line is basically an expectation over a max. So that's what a regular MDP is. So the next one is a min instead of an expectation over a max. And then the third one's an expectation over a p-ordida, which is
yeah,
thing.
sorry. I just made up some notation there. Let me explain what that means. So the basic idea is that we're going to take a weighted combination of all the actions, and the weights depend on the rank of the action. In particular, we can have a weight for the max and a weight for the min and a weight for the second largest and third largest and fourth largest, and those weights are consistent. They're going to be just a constant.
Oh, okay. Does that imply that we have, no matter where we are, we have the same number of actions?
Yes.
Okay. Is there any relationship between those weights? They can be negative, they can be a million, they can be anything we want.
Sorry, yeah. So good. So the row of the weight for a given rank should be it should be a convex combination. They should all sum to 1 and be non-negative.
Okay, sure. So we're gonna. It's like doing an expectation, but based on how good the action is, sort of.
Yeah, where it falls in the list. Yeah. So this actually generalizes the first line, max, because a max is what we get if we put the row of the largest rank to be 1 and the row of everything else to be 0. But it also lets us get min, right, where we have the row of the smallest rank equal to 1 and everything else 0. And, everything in between, like, uniform weighting over all the actions.
Okay. All right. I think I got it. And let's double check the last line. The last line, it's an expectation over minimax. I think I know what that means. Okay.
Well, just to make sure. So it's a little bit weird. I'm kind of abusing notation here because minimax is usually defined when you've got two different actors, kind of a player
Hmm.
one and a player two. And here I'm just writing it as if it were one actor, but you should think of it as this A prime represents a joint action by the two players.
All right. Okay. I think I got it, or at least got it enough to work it through.
All right, why don't you give it a shot? And you know, and if you don't get exactly the way I was thinking about it, that's okay. It's mostly to just sort of get you thinking about how we're substituting in different pieces to get this generalized MDP.
All right. I like it. Okay. Go.
Okay, Charles, what do you think?
About what?
Let's just go through the ones that don't have names yet, and give them names. You know, kind of think through what it is that they are like and label them.
Okay, sure, we can do that. All right, so if the first one is a regular MDP, and what makes it a regular MDP is that you're doing an expectation over the next best action that will be taken, right?
Right, the best next action, I would say.
Right, right. That's right. That's the right way of saying it. So here, the only difference between the second one and the first one is that instead of doing an expectation, you're going to only pay attention to the worst possible state you could get into.
Mm. Okay, and so we're taking out the actual stochastic dynamics of the MDP and replacing it with something that is minimizing.
Right. And so that means if we were thinking about the function at the very top, the Q star is not, kind of the value of taking an action in a particular state, given that you're then going to do the best thing from that point on. But it's sort of the value you would get if you sort of always assume the worst thing could happen.
Mm-hmm.
And if that were true everywhere, then you would be valuing things by the worst possible outcome. And so that would be a kind of, oh, I don't know what the right word is, maybe something like a pessimistic MDP or a risk averse MDP, something like that.
Ooh, good. Worst case MDP, maybe.
Mm-hmm. Yeah.
It's also related to, in control theory, the notion of H infinity control. H
Huh.
infinity control basically says, I don't know what's going to happen, so let me assume that the worst thing's going to happen.
Okay. So pessimistic sort of describes the outlook on the world of this equation. But is risk averse the right thing? This suggests that I will end up trying to choose actions that put me places where the least bad thing could happen.
Well, I mean, I wouldn't quite think of it that way. So it's almost as if the environment is out to get you, right? So instead of just randomly transitioning you to some state, it's always putting you in a state that makes you the least happy of all the states that you could go to.
Oh, so grad school.
Well, it depends where you go to grad school. Like Rhode Island is a pretty good state. All right. So we're going to be placed in a state that is worst for us. And once we get there, then we get to choose an action. We get to choose the action that's best for us. So it's almost also a kind of game, right? Where we get to make a move and then the environment makes a move and then we make a move and then the environment makes a move.
Okay, I like that. I like that. But that means you would want to choose the action that would get you to the place where kind of the least worst thing could happen.
Yeah, that's right. Right. So the agent, the ones who's doing the deciding, is trying to be risk averse relative to what the environment might do to it.
Right. Sure. That makes perfect sense. Okay. So risk averse is not a bad description.
Good. So other answers that I would accept for here include things like adversarial dynamics or two-player game, things like that. I guess you could also notice the way that this is written here. This is the min over all next states. So this is really going to always transition us to the worst state, not the worst state that makes any sense, because we didn't do something like, for all states in the set of states that are reachable with probability greater than 0, right? That's a little bit more constrained. We didn't constrain it. So really it could just be an MDP that makes you sit in the in the worst possible place and just pummels you over and over again. But I don't think there's a nice succinct name for that.
I thought that was pretty succinct what you said.
All right, good. All right, you ready to move on to the next one?
Sure. Okay. So the next one, we've got our expectation back. That makes me happy.
Yay.
So we got our expectation back. But now what we're doing is the next thing that'll happen is rather than doing the best action from that point on, we will take an action, we'll take sort of the average over all possible next actions,
Hmm.
but give more weight the better the action is, if I remember what your row of ORD actually does.
That is a nice way to do it, but this is not written to be that way. It's just weighting by the ranking. So it could be that we put higher weight on higher ranked things, but it could be we put higher weight on lower ranked things too. So this is a very kind
Oh.
of a very general expression. But you're right. I mean, this would be useful in the case where it's doing some kind of, I don't know, maybe a generalization of epsilon greedy exploration,
Mm-hmm.
right? The idea that we're going to, with highest probability, choose the max, and with lower probability, choose things that aren't the max. So it generalizes that idea.
Right, and so actually that would be nice because one of the things about the way we go around learning MDPs and do Qlearning and value iteration is we kind of assume we're always going to do the next best thing, but since we still have to do exploration as well as exploitation, that isn't actually what we do. So this would allow us to do exploration.
Well, it's not that it's allowing us to do exploration, it's actually defining the values so they incorporate exploration into them.
Right.
So one way of thinking about what this is an exploration sensitive MDP.
Right. That's exactly what I was going to say.
Oh, awesome. Well, just to finish this thought, the values that you define for the states include in them the probability that you might take a non-maximum action. That's in the sense in which the values are exploration sensitive. We can explore in, say, Qlearning and still use this first update rule to try to figure out what the value is for the best policy. This is actually trying to figure out what the value is for the policy that is exploring.
Right. And in particular, the policy we're going to follow as opposed to the policy we could follow.
Yeah, that's a good point.
Right. I think that's important.
Yeah, so this is kind of neat because unlike regular Qlearning, it's actually figuring out the value. It's on policy. It's actually figuring out the value of a policy that we might really be taking. Whereas if we were to literally always take the max, we won't learn the right value in the case of Qlearning, right? Because we're going to get stuck not exploring.
Okay. I like that. I can't think of a better name, though. Are there any other names for this besides exploration sensitive?
Well, as I said, it generalizes max and min. You can one of the things that I really like but have absolutely no use for is that you can imagine an update rule where you always are trying to choose the median action, kind of not too good, not too bad, middle of the pack. I guess it's kind of like the decision process for people who just want to be mediocre and not stand out. So I'll say mediocre.
Mediocrity sensitive MDPs.
And there's another case where I found a use for this, which I think is kind of interesting. So imagine that we've got a huge action space where actually computing this max is going to be difficult.
Okay.
So instead of actually running through all possible actions to compute the max, we're going to take some random sampling and then just compute the max of that random sample. So does that make some sense as an algorithm? Like instead of taking the max over everything, we'll just take a max over a handful of things.
Sure, that makes sense if you have, for example, an infinite number of actions.
Yeah, that's right. Or even just a very large number of actions. The first time I heard about this was in the case of an MDP that was being used to define scheduling actions for the space shuttle, back when there was a space shuttle. And there was just so many of them that going through them was intractable. So this is Tom Dietrich's work. He actually randomly sampled some of the actions and then chose the best among that sample. So what that gives you actually is there's some probability you will choose the actual max, but there's also some probability that you miss the max and instead get the second largest out of all the actions. And there's some other probability that you get the third largest of all the actions. It's more likely that you get higher ranked actions than lower ranked actions, right? Because of the subset that you choose, you're always taking the max of that.
Mm-hmm.
But it's not going to be with probability 1. And so what you end up with is this some kind of distribution over the likelihood of choosing the max and the second highest and the third highest and so on. And this equation generalizes that idea and shows that if we use this as our update rule for something like value iteration, we get a well-defined answer, right? This will converge to something. It's just a little bit hard to say exactly what it converges to. It's not the best possible policy. It's more like the policy that we get when we always choose the best action from a random sample.
Right, but if there are a bunch of pretty good actions, then you may not get the optimal policy, but you'll still get a pretty good one. It's like being satisficing as opposed to satisfying.
Ooh, yeah, I would accept satisficing as an answer for this one. That's cool.
Okay.
Last one.
So the last one, we have our expectation again, which I like. And now we're going to do minimax. And what you said before we started going through the quiz was that, you're kind of treating this as sort of a joint action space. So it's sort of you taking an action and then your, let's say, opponent taking an action, and so on and so forth. And so really, I don't know what I would call this, but it looks a lot like just regular old game search when you have, a zero-sum game.
Yeah, zero-sum game. That's exactly what I would call it. And we're going to talk a lot more about variations of algorithms that act like this, that deal with the case when there's multiple agents. But this was sort of a nice setting to bring it up because the basic result says that if we've got a generalized MDP, we've got this operator and this operator defined in such a way that it's a non-expansion. And it turns out all these things, minimax, this rank-ordered, rank-weighted idea, max, the linear combination, expectation, min, all these things are all non-expansions. So all these things, value iteration will do something reasonable. It'll actually come out with a fixed point in the limit.
So actually, min, max, all of these things, and ord, row of ord, they're all convex sums. So does this mean that all convex combinations are non-expansive?
So that's a great question. They are all convex combinations. That's true. It is not the case that arbitrary convex combinations result in non-expansions. In particular, if the weights of the convex combination depend on the values, the actual magnitude of the values in some way, then we need not get anything that is a non-expansion.
Okay, so that's good to know.
Yeah, and that actually comes up in a really important setting, which is if you're doing not, say, epsilon greedy exploration, which corresponds to the third line here, but instead we're doing something like Boltzmann exploration, we could run into trouble. All right, so I think that's it for this kind of introduction to generalized MDPs, and I think that actually finishes the section on convergence. So you ready for some recap?
Yes, I love recapping.
All right, Charles, so what did we learn in this extended unit on convergence-related stuff?
Well, I think the first thing we learned was convergence. Convergence is a thing, and it's something that we would like to be able to prove about our algorithms, and we can, in fact, prove them about some of our algorithms.
Like what?
That, for example, Qlearning actually converges. It doesn't just converge to something, it converges to Q star.
Oh, yeah, that's pretty good. Now, we did that in the form of a generalized theorem that broke the Qlearning rule down into actually kind of two little sub-update rules, and the proof basically says, well, if both of the sub-update rules do the right thing, then the overall update rule does the right thing. And that got us that Qlearning converges, and as you said, not just converges, but converges to the optimal Q function for the corresponding MDP, which actually is pretty amazing when you think about it, right? We have all these algorithms for solving MDPs, and Qlearning is like one line of code that just says, whenever you make a transition, do a little update like this. And nonetheless, this actually that actually works. That in the limit, it computes Q star. It's almost too simple not to try Qlearning.
Right. I mean, but hey, it's generally the case that simplicity is often the right thing to do. We call that elegance.
Ooh, nicely said.
So what else did we learn? Okay, so I learned some other words like non-expansive.
Or even better, contraction.
I do not like that word.
Really? It makes you uncomfortable?
Okay, so the last thing that I remember us talking about is speaking of generalized MDPs.
Right, and generalized MDPs have this nice structure that as long as the operators that are inside of it that are doing updates are not expansions, then we get these other kinds of convergence. We get the convergence of value iteration, we get the convergence of Qlearning. So we can actually combine these generalized MDPs with the generalized convergence theorem, and kaboom.
Yeah, and that's actually pretty cool because it would allow us to think about different kinds of decision processes, different sort of situations we wanted to be in, and we would know that all the math would go through, and so we could just do it. All we have to do is worry about whether they're non-expansive or not.
Right, exactly. And there's a whole set of things that we've shown are non-expansions. Oh, maybe that's even worth remembering. What are some things that are non-expansions?
Max.
That's a good one.
Min.
More generally, order statistics.
Yes, order statistics.
Fixed convex combinations.
Mm-hmm. That's my favorite.
Actually, I think all the things are kind of variations of those too.
Yeah, I think so.
You can get fixed convex combinations of order statistics, so we can actually combine those two things together.
Oh, that's cool. Is there anything else? I think that's all that we covered, yeah.
Cool.
But I think importantly, you said something that I think was important, which was that not just any convex combinations, but it has to be fixed. That if the value of it can change, like with the Boltzmann exploration, then you do not know that it will converge.
That's right. Yeah, and it's actually kind of maybe an interesting open problem. It is definitely the case that we can prove that Boltzmann updates are not non-expansions. They can be expansions. But that's not quite the same as saying that therefore it doesn't converge. And there are some examples of Qlearning like update rules that have update rules that are not non-expansions, and yet it converges anyway. There's one that I was involved with really recently that we called Coco Qlearning,
Of course you
which
did.
is a two-player game setup. And that one you can show that it's not a non-expansion, but it converges anyway. Shoo.
Oh, okay. So look, one last thing, and I think we've covered everything, but one last thing, I realize we have an open question.
Okay.
So up on the very first line, you have convergence. And it's not just convergence for Qlearning, but the Qlearning actually converges to Q star, which is mildly miraculous. So are all these other things that we were looking at, these generalized operators and the order statistics stuff, those things converge, but do we know what they converge to?
Right. Yeah, they converge to that which they converge to. So in general, it's
Hmm.
not Q star, right? Because we're actually defining a different set of Bellman equations. So it actually is defining a different fixed point. Um, in some cases, those fixed points have good names. In some cases, not so much.
But do they converge to something that looks like the corresponding Q star? If you know what I mean? Do you know what I mean?
Yeah. So the idea is that they'd converge to something that makes sense with regard to how the Q equation is defined. So, for example, if we replace the max in the action selection with some fixed probability distribution over actions, that's kind of equivalent, or maybe even is exactly equivalent, to having a fixed stochastic policy. And what we get convergence to in that case is the value of that policy.
Okay. So that's good. That's a big win. All right. So did I forget anything?
No, these are the things that I think were the critical high points of this fairly formal section, right? We did a fair amount of proving of stuff. I think we're going to do a little more of that before we get into some more implementation and practical stuff.
Okay, cool. So then you'll be doing those.
Yes,
That's great. Well, then I look forward to next time.
awesome. All right, thanks, Charles.
All right. Bye.